And then if the recording saves here, I can come back.
Or I can have a look if I find it. I'll let you know.
Yeah, no problem. Then I think everything should work.
Thank you, Emma. Thank you very much.
No problem.
See you in charge.
Yes,
I
indeed.
guess it's the job as lunch talks for you.
You're the experts. Thanks very much.
See you later.
That is unavailable.
I want to make sure that I
Yeah,
can
you can see the participants somewhere.
Yeah. Hello, Berta. Can you hear me?
I think you don't need to unmute you can keep yours on mute.
And your sound comes from there.
Hello, Berta. Can you hear me?
If you click on participants up there at the top.
Yes, I can hear.
Yeah.
All right. Great. So we can start. That's okay with everybody? I'll tell you when it's 25 minutes if you need. I can keep track of the time.
Yeah.
So thank you very much. You're going to give us a talk about your master thesis with neural networks and emerging galaxies.
Yeah.
Thank you very much.
Welcome to my master thesis defense. I'm Untitled Chapter, just to know myself a little bit better. I'm a Peruvian guy of 32 years old. I did my bachelor in physics in Lima. And yeah, now I will introduce you my master thesis presentation. The title is Identifying Galaxy Mergers. Identifying galaxy mergers in the Hubble Space Telescope and James Webb Space Telescope images using convolutional neural networks. Maybe a little bit of introduction of this is why we are interested in detecting galaxy mergers. Is we all agree in the lambda and CDM model that big cosmological structures formed by smaller successive collisions of smaller objects, and this can be gas, which are bound in a specific gravitational field, mostly by dark matter, and they collide and they start to form bigger objects like galaxies. That's one way of galaxy formation, but also because of this chaotic system that still continues, it's more likely that you have also collisions of galaxies. So actually this happens, galaxies absorb the neighbor galaxies and they create more galaxies. So, so galaxy mergers is indeed one of the ways to understand the formation of galaxies and also other phenomena related to galaxy evolution. Actually, there are multiple studies which connects galaxy mergers with phenomena happening in a galaxy, for example, star bars, black hole growth, quasar activities, star formation rate, etc. So that's why detect them, galaxy mergers is that relevant to understand the galaxy formation and evolution. So I will jump directly into the methodology. So this is basically a slide we explain in a very big overview what I did this year basically. So the first point is to get labeled the data. So I use simulated data. When I say label data, is data or images of galaxies which has a label. So you say this image represents merger processes happening, and this image no. So from this label data, you train a model. So the model see these features from these images and learn from it. When the model has learned, then you use this model to make predictions on real images. So in this case, we apply this model into the HST and James Webb Space Telescope images. And then we compare these results. There will be a lot of mismatch in terms of predictions between these two sources. So that could lead to many interpretations. Why is that difference happening? But what I will focus more is just on the wavelength difference between these two sources. And then we will discuss the conclusions. So that's it. So jumping to which kind of data I use to train the model is basically the Illustris TNG project, cosmological hydrodynamical simulation. The way how we observe this simulation and how we extract these galaxies from this simulation is using parameters which are closely related to the hypersupramica HST survey seen in the E-band filter. So this is a ground-based telescope located somewhere in Hawaii, I think. But the most important thing here is because it's from Webb telescope. So it's like we are observing this simulation happening in this kind of telescope. So parameters like the point spread function, depth, pixel resolution, background, and probably some more will be, of course, far away from the space telescope, like the Hubble or like the James Webb. Because we are observing this simulation with these parameters in the E-band field, where is basically this range of wavelength, which is mostly some optical and infrared as well. So that's how we are looking into this simulation. So looking just into this, of course, we are not having simulated data which are at least very closely to the images that we will make predictions on, like the HST of the, right? Yes. Now, the simulation contains a lot of images, galaxies, which we have split then into redshift beams. So you have here 1, 2, 3, 4 redshift beams. This and this and this, and this one comes from the Illustris. This is a special case. This image galaxy comes from another simulation called Horizon. I will not go too much into that, but it's really interesting to see some insights also related to this one, which basically the main idea of taking images from another simulation in the same redshift beams than this one is to see if the parameters of predictions are better or worse and how worse they are, right? So these are the groups of images that I've been training and testing the model. The first one is the lowest redshift beam, which is this one. This is the greatest one, contains 120,000 images. These are the dimensions per image, pixel square. And this is, because this is a big one, this one I split 80% for training, 10% of these images has been used for validation, and the other 10% for testing. And the rest just testing mode. So I just made predictions with the model that has been training with this image, which was in the low redshift. Another important thing to know here is that all the simulated images are in between redshift 0 and 1. In the Hubble and in the James Webb, I would have images until redshift 4, for example, right? So that's another thing to take into account. So these simulated images, I also got a small catalog from this. This is the most important part of the catalog, which basically defines me what's a merger of the image or not. These are labels, which are defined as a 1 or 0 per image, telling me if it's a pre-merger or if it's an ongoing merger, post-merger. And these definitions comes from if image is a pre-merger, means that this is in a merger process, before a merger process, 0.8 gigayears until 0.1 gigayears. And if it's an ongoing merger, it's in the window of 0.1 plus minus gigayear in a merger event. And if it's post-merger, in between this window of time. If it's a major merger, means like if it's either one of these three, then it's a major merger. Otherwise, it's 0. It's no merger happening at all. So all these images, we have a label specified, which is 1 of 0, depending on the flag. These are just some random examples of how that images looks like. I just wanted to show this really quickly because then you have an idea how these images looks like. So it's just a square. In this case, this is 320 pixels square. And the main point to show this is that the images, that the mean object, so the mean galaxy is always located at the center of the image. And depending if it's a merger, these are merger samples, these are no merger samples for this specific sample data set. Yeah, that's the relevant thing, that the mean object is always at the center of the images. And depending on the label, we say that that central object is in a merger process, ongoing merger process, pre-merger process, etc. Yes. So to make our trainings, first we have to define what is a merger or not. So we have multiple classifications, but we only focus to have a binary classification. So we want to know is a merger or is not a merger. That's it. We didn't do analysis between these three flags. So for that, I did two main group of trainings. One is related to the definition of merger in this way. So if it's a major merger, it's 1. If no, it's 0. So if it's either of these three, I say it's a merger. If not, then 0. And the second group of trainings, I may, if it's ongoing merger, oh, of course, merger, then it's a merger process, otherwise a no merger. So meaning that in this group of trainings, I'm discarding the pre-merger process, which makes us feel like all the images that we will have here classified as mergers are the most obvious mergers, because probably we will see some tidal deformations, which the model can identify better, right? Because in the pre-merger, well, you can have two galaxies there, like it's in a pre-merger process, but probably it's not enough features that the model can see, which can learn from this. They can say, oh, this will be a merger. So that's why we did these two different group of trainings. Yes. So the images that I showed you 2 slides ago, basically is each image is a feeds file. So the data flow of what I did with these images is as follows. You have a bunch of feeds files. And in this case, if we want to train a model, you have to pre-process these files. So in this case, the pre-processing part that I did is mostly crop the images, do a zoom. So focus on the central part of the image, which is my main object, my galaxy that I want to see if it has some kind of deformation. And then normalize the pixels values. This could be, I mean, the normalization of the scaling can be multiple ways, depending on what you want to emphasize in your image. In this case, I just use the logarithmic normalization of the pixels and the 0 to 1 scaling of the pixels after this, in this process. Then after that, doing some data preprocessing of the fields files, then I create a TensorFlow data set. And then I just train my model or make my predictions. The model basically is the CNN architecture. So this purple thing, let's imagine there is a single feeds file. It's one image of the galaxy that I showed you previously. And the convolutional bar, so the CNN, what it does is extract features from this image. So the convolutional bar basically will play an important role here. So it basically, what does, if we imagine that this is our galaxy image, you take one filter and you map specific regions of these images, and then you extract the patterns that are here into another smaller matrix. So that's a convolutional bar. So you can have multiple filters. You can define how many filters you want to use. In this case, we use 32 filters. So you have 32 multiples of these small matrices, which in some sort of mathematical operations with your original images will result into a smaller image, which basically contains the information of some features related to this image. So if you use 32 filters, you will have 32 of these outputs for a single image, and each of these 32 will have a single specific feature pattern extracted from the original image. It can be a specific peak tidal or whatever, morphological stuff from the galaxy. That's the convolutional bar. Then you do some data preprocessing more related to some pixel scales or mapping, pixels mappings. And then comes the convolutional bar again and again and again and again. So you will have multiple smaller matrices, which will contain information related to your original image. And then you put all these, each pixels into single neurons, which for a specific weight are connected to the output label, which can be 1 or 0 for what we define what is a merger, right? So the input and the output are values that we know in order if we want to train a model. And all what is coming here, the architecture also we define, but there are some weights and parameters that we don't define. I mean, the model will define them by themselves by looking at this and training the model, right? Putting images, the model will extract the features and will tune the weights, because the connection between and this, there is a weight connected here also, which kind of filters we use. There are some parameters that the model will train in order to make very good predictions. So then you will get a picture like this, which basically these images, the laws can tell you to how far you can train the model. So you can see if this is not going lower anymore, then you can say, okay, my model is stopping learning, it's not learning anymore. We'll stop the training. And if this yellow line separates from the blue line, it means that your model is overfitting. So it means that your model is not learning at all, it's just memorizing the images. So the memorization of the images means like if you put new image into the model will not make good predictions, right? But if you put the image that the model has seen before, it will predict really well if it's a merger or not. So that's an overfitting case. Yes, that's basically a very big overview of how this convolutional neural network works. When you make your predictions from labeled images, you can build a confusion matrix like this. So the true labels are my images are merger or not merger. So that's how I define them originally. But then I put these images into my model, and I want to know what my model tells me about that. And that's basically the predicted values. So this number, for example, means that I have 1,560 images that I know they are mergers, but my model say also they are mergers. But then I have this number that I know they are mergers images because that's how I define them in my simulation, but my model tells me it's not a merge. So and so on. That's how a confusion matrix looks like. That's the kind of information it tells you. From these four numbers, you can have or define multiple parameters in order to say my model is doing good job or not. Some of these are completeness and reliability, and the F1 score. The completeness basically is the fraction between this number and the total, which basically tells you how many real mergers are correctly classified as mergers. And the reliability is the fraction of this number between this total, which basically tells you how many of the total predictors of mergers are actually real mergers. So with this, you can assess your model. You can say, my model, yeah, I'm happy with it. Let's continue. Now let's make predictions on the real images because I'm comfortable with these values. Yeah, the F1 score is another metric which basically combine these two, is the harmonic mean of the completeness and reliability. So the best values for these two is 1, the worst is 0. So if these two are, if either of these two are 0, this is 0. If both of these are close to 1, this is also 1, right? So if you want a metric that can help you to have a good completeness and good reliability, probably F1 score will play a good job. Now, these metrics are really important because when you want to know if your model is performing better, you want to say, okay, it's performing better at Webb. Here, and it depends what kind of analysis you want to do, right? This is one of the insights I took for one of the analysis I did. So here, for example, in all the data sets for different redshift, what I did is create signal to noise aggregated groups. So for this snapshot, Snapdoon 5057, which is the highest redshift, almost close to 1. What I did is create multiple data sets from that single data set. So I filter all the images with signal to noise more than 0, put it into one data set. Again, filter the signal to noise more than 5, another data set, signal to noise more than 10, another data set, aggregated signal to noise groups of data set for each of these groups. And then just make predictions with this. And because these are test data sets, I know the real labels of this. I mean, I know how the simulation classify them. If they are mergers, ongoing merger, force major, and I know what they are. And then I compare with my predictions with the best model of the group 1 of training. And then I can get the metrics that I show you from the confusion matrix, the completeness, reliability, accuracy. And that's basically what I'm showing here. In aggregate signal to noise beams. So what we can see here for completeness, for example, is that the completeness here increased by redshift because it goes redshift from -2 to 1. So this is high redshift and going redshift down, right? It increased in this case. Doesn't have to do too much with the redshift, but it has to do because this model that is giving me these metrics has been training with the data coming from this data set. So from the purple, from 7891. So that's why we see a very good performance here. Another thing we can see here is that completeness increased over signal to noise a little bit. So if you look, for example, to the red one, it goes higher and higher over signal to noise aggregated value. That's another thing we can look into this plot. Another thing we can look in this plot is that this test set too, which is coming from another simulation from Horizon. has a very low value of signal of completeness, even though it comes from the same redshift group of this one, of the purple one. And this has to do with maybe this another simulation is not taking into account some parameters that the simulation, the other images we are using. We can understand this, and we did this by purpose because we wanted to know how good or how bad our prediction on real images will be after doing this job only with simulation images. Simulation images is not the same as real images, so we knew already it will be this mismatch. So we wanted to know how bad it would be. So that's why we took another simulation called Horizon, and we see, yeah, indeed, it's lower. Yeah, that's one of the things I can point out here in this plot. When we have our model, what we did directly is to make predictions then to the HST and James Webb. I will focus on the wavelength range. So in the HST, basically this is still infrared. James Webb also infrared, but a little bit more far infrared if you compare. But depending on the what redshift object you are looking, of course, you will be looking here at infrared, but the emitted wavelength could be optical or even ultraviolet, right? If it's a redshift 3, 4. This, if it's still a redshift 3, 4, this object that you are looking, it will be still in infrared. I have another plot that shows that. So for the HST, I use the candles UDS total combined image being observed with the wide camera 3 using a F160W filter, and from the James Webb, I use the near cam in the longest wavelength channel. So when I apply my model that has been learned with simulated images on the real HST images, I got a prediction histogram. So these are all the predicted values. So what the model gives you when you try to make predictions on HST or whatever image is to give you a probability how likely is that that image is merged. And those basically are the probability values that give me as an output when I apply the model to the HST. So this is no binary. This is not like this is a merger or no. It's just probability range. So we need to define a threshold here to know what is what we say when we say an image is a merger or not. It's after 0.5. So then we say all these images are mergers, and this no, or is here, or is here. Where? How we can do that? So that was the tricky part. And for that, I have to by force do another validation on these values on the real images using a visual classification. And this is basically coming from a rainbow database, which some experts basically visually classify and vote for a specific flag, whether it's a merger or no, in images visually. So this is basically probabilities of people just saying, I think this is a merger, I think this is not a merger, and then they take the average for a specific image, depending on how many people vote. And then they have a probability range here as well. Of course, they didn't vote for all the images. The number of images that has been classified as a merger or not visually by these experts, which is in the rainbow database, is very short. As you can see here, most of these are being classified as non-mergers, and some of them as a merger by everyone, and some in between. But I wanted to test this. I want to know what will be the threshold. So the problem of validation of these images basically translate into which is the best threshold that gives me the best F1 score, taking into account that this visual classification by experts is real true values. So that's the complexity of this. And for this, I have to create multiple threshold for loops, multiple values of threshold, then compute the completeness and reliability F1 score, and then do the same process for different threshold values. And because these values of completeness and reliabilities has to be done on a balanced data set. A balanced data set means that you have the same amount of mergers and non-mergers. I have to drop some of them in order to make the balanced data set. So for each value of threshold that I took for either of these both, I have to, again, on top, take like 42, I took 42 drop states in order to balance it. So for each drop state, I got F1 scores, and then I took the average of them. So having done all that analysis, I came with a threshold value here, which is 0.05. So that means that the best F1 score was 0.6 almost. So that means that the best threshold value to define here in order to say after that value, I say it's a merger, and before that value is no merger, is this one. Having seen the visual or agree with the visual classification from the rainbow database. So this value is very low. So I was a little bit weird that it was very low, but still could distinguish what's a merger or not using this visual classification. So with that threshold value, then I made predictions on the James Webb images. Again, I got something like this, but using this threshold, 0.05 somewhere here. After that, I say all these images are being classified as mergers, and before that, no. So then I end up with this matrix. This is not a confusion matrix. This is just a comparison matrix or table that shows how many images in the James Webb has been classified as merger or no, and similar in the HST. But also compare between these two. So there are images that has been classified as mergers in the James Webb, but as a no merger in the HST. There are 646 images that have been classified as a merger on the James Webb, but also as a merger on the HST, and like that. Yes. So from this mismatch, so why there are images being classified as merger in the James Webb and not in the Hubble, and the other way around? Why? Yeah, we can discuss here very much, but I only focus on the wavelength range. So if we remember the wavelength range of the Hubble and the James Webb, these are the filter details, and if we put this range of wavelength together at redshift 0, we look something, or will be located somewhere here. So looking images at redshift 1, 2, 3, 4 will means that these filters will capture light coming from objects which are emitting at probably ultraviolet visual from the HST, but from the James Webb still will remain into the infrared. So this is related. This can be related to some phenomena that's happening in the galaxy at this wavelength range that we observe in the HST. But in the James Webb, still we are still into this infrared range, which means that of course we are observing galaxy phenomena which emits light at that range at the source. This is another comparison histogram which basically shows the number of mergers depending on the redshift beams. And this is really curious because it's always like, it's not depending on the redshift, how we make prediction of mergers in both sources. So at any redshift, always we see like the number of mergers in the HST is like double than the James Webb. And here basically are just some examples of images of being predicted as a no mergers on the James Webb and no merger also in the HST. So we see always here dot sources. The models say in both cases it's just no merger. Here they say it's a merger. So we see they're a bit more clumpy curves. But this is a little bit more interesting because here are images that the model say is a merger in the HST, but not in the James Webb. Probably this is a more clear example. Here we don't see it so clear that there are two objects approaching. Here you see, but also you have to take into account the size of the images. The images of the James Webb looks like more zooming into the center than the HST. That also plays a very important role. I did an analysis on sizes of the images and how the model performs, and that also play a very important role in how the model performs. Here are some examples of James Webb mergers and HST no mergers. And James Webb, we see, for example, this image looks more clear than the HST, infrared, but still looks on some deformation that the model think, oh, maybe this is a merger, a process which happening or is still happening. This is not clear to me why the model says a merger, but yeah. it says. It gives a certain kind of probability. So in conclusion and limitations, well, simulated images does not represent reality 100%. The image preprocessing is a very important role, the size of the image also, because the neural network, of course, doesn't know, I mean, what filter you use or what size you use. I mean, it will look pixel by pixel and the location of the pixels. So if you zoom your image more, the performance will be totally different. Also, the architecture of the CNN play an important role. How you process all these pixels depends very much on how the model will be learning. Another conclusion is the signal to noise and redshift correlates with completeness. That's what we saw. And the redshift doesn't seem to correlate in the comparison ratio between number of mergers and no mergers in the HST and James Webb. So yeah, the number of mergers between these two sources going in redshift, we see always that the HST is like kind of double than the James Webb. Some images at high redshift might contain information of mergers even at infrared. So why we have number of mergers in James Webb that are not being detected in the HST? Why we detect mergers at infrared? If we know that merger process might contain star formation, chaos system, like can emit very short wavelengths. One explanation for this might be that these short wavelengths might be get absorbed by dust or scattered somewhere. So we don't see that very short wavelengths when there is a merger of galaxies, but we see at infrared by the James Webb. That could be one explanation. And yeah, that's it. It went pretty quick. Thank you.
Perfectly on time.
Yes.
Don't feel like it went quick. I give the floor first to the questions to the second examiner, Manuela.
Thanks a lot for this nice presentation, and it was very nice to see your results. I have a couple of questions, but okay, I will start with the first one. So if I look at your slide 6, if you then go to slide 6. Yes, I noticed that you have used your training, the sample that you use for training, validation, and test does not have the same redshift with respect to the samples that you use for testing. So I was wondering if you are sure, or how do you make sure that this choice doesn't introduce a bias in your method? And do I interpret correctly the plot?
So the reason that we choose log redshift, yeah, I don't get it, because I mean, if you if we train the model into this redshift, of course the model will perform different here and here and here, and of course in the James Webb and HST. So the only place where the model will do like a perfect job is on images which are here, because you use this to train the model. So yeah, so if you have a model trained here, there will be always a bias for all other, even at redshift difference. Yeah, we saw that in completeness and reliability are different for the other redshift beams. So there will be always a bias.
Can I quickly ask why? Because I mean, merger is a merger, I guess. So why is there a bias going to the redshift?
That's a good question. But the redshift, I think, has to do with resolution of pixels. I mean, if something is more near, probably you will see more clear features of mergers going on than if something is like far. But that's how I see it. And the CNN one takes its features in pixels, yeah, in pixel size. But yeah, I see that in that way. Probably has to do with the distance, so that the features are not being well recognized. Then, if you train the model using this specific image, I think has to be with that. So the model basically will look at features that are here at this scale, but at other scale, other distance, these features, of course, will not be like the same.
Go ahead.
But that's how I see it.
So you have developed a very nice CNN, but a posteriori, now that the work is concluded, what do you think are the main limitations of the actual network, and how would that be possible to improve it?
Okay, the network itself, because one of the main limitations is using simulated data, which doesn't really represent closely what the HST or JWST give us. So first of all, we're using simulated images, which from a ground-based telescope. But talking not about the simulated data, but about only the CNN, how we could improve that, only looking at architecture. Yeah, I didn't do a full analysis on the images in terms of where the CNN is looking at in order to say this is a merger or not. That, for example, would be a very good analysis, which I didn't have the time to do it. So then we know in which regions of the picture of the images that the model is saying is a merger, in which parts you can do that. The model is looking at or is basing his predictions on. That could be one thing that could help us to improve the CNN architecture, for example, so we can probably change the number of dense layer or drop out number, 0.5, but probably another hyperparameter. But yeah, there are multiple hyperparameters in the model that we can tune. But yeah, I didn't do the analysis, so I cannot tell you probably if we tune this parameter, it would help. No, I did, for example, for the second training of groups, I did like 29 experiments, changing the loss function, learning rate, changing the convolutional layers, how many convolutional layers we had, taking out the dropout, putting out dropouts in some parts. And for all of these multiple experiments, changing multiple parameters, I got the accuracy plot with the loss plot, but I only use the best one here because most of them I use overfitting and traces that. But doing a specific analysis on the images and then say, okay, because I see this on these images, this hyperparameter has to be changed. I didn't go so deep into that yet.
Can I ask why you used this method in the first place? Why CNN? Why did you choose to use this method?
Well, the CNN in the world of data science, I think, is one of the most common and famous and very robust neural network methods in order to detect or to classify images binary. So, yeah.
Because of its methodology.
Yeah.
So was there a choice? Did you have other choices to make, or?
Initially, at the first week, I think I came with one. But yeah, I mean, the short was really short, so I really stick with what my supervisors, or we work in collaboration. And this is, even though I made a lot of progress here, there's still a lot much to do. And it's a very interesting topic. But yeah. Yeah. Yeah, if I came with my own models, probably it would give me more time. Yeah.
That's where the algorithms actually come from. So it's somewhere there's a database where there are algorithms, or
Algorithms was provided, but mostly by Verta. The main structure. Yeah. Also the simulated data I have. We didn't do analysis on simulated data that looks closely to the HST of the JWST because that also will take much extra time to make that possible. So we use what we have available. So yeah, I use the Peregrine and the Hubble cluster also to make the simulations.
do you have more questions?
Yes, if I can ask, it's more a bit of one curiosity and one question. So the algorithm that you wrote, in the end, you coded it in Python or in which language?
It's Python TensorFlow.
Ah, okay. Yeah, sorry, you're right. You mentioned that. And I'm not an expert in the field. One curiosity, basically, if I understand correctly, then the limitation of this work comes from the selection of the simulated images that you use for the training. Would it be, again, a posteriori, because at the beginning you don't know, but now that you have done the study, have you identified for the next time a different set of images that you could use for training which look more promising? Is there anything on the market, let's say, that looks more promising than that now?
I'm not sure, but what I hear from Berta, which is the person that she was on Zoom, she's the person she provides, she told me that it's possible to generate this, but it will take an extra time from the same program. I heard, yeah, from the same simulation software.
Excuse me, I didn't hear you. Can you repeat?
I
Yeah.
mean, this is the Illustris TNG project. So what I understood from her is that you can generate here the physics going on in the universe, so that the gas joining and then from galaxies and the galaxy margins and all that kind of things. But also you can say how you want to observe them. So the images that I've been using has the parameters of observation similar to this survey. What I understood from her is that also you can say I want to observe it like I'm looking to the HST, for example, or something like that. Probably that will improve, yeah, indeed. Yeah.
Thank you.
Other questions?
In your comparison between HST and James Webb images, did you take into account differences in instrumental resolution?
I didn't did any analysis with the instrumentation here, just wavelength, but I mean, of course, the images that I took has different resolutions, but I mean, I didn't use this information to make any conclusions.
So
Just at the
I
way.
imagine you could, there must be differences in image resolution. Both telescopes have diffraction limits. And the wavelength difference is not that big. Telescope difference is factor 3. There must be an intrinsic difference in resolution. And I could imagine that to make a proper comparison, you would have to convolve one set of images to the same resolution of the other set of images before you can draw any conclusions.
That's true. That's true. The way that I went is using signal to noise in this case. So I filter, I use signal to noise to make this jump from one data set to another. But the resolution is indeed another parameter that, if I would like to continue this, of course, I would like to take that into account. But looking into the resolution itself, the images of the HST is 0.06 arc seconds square per pixel. No, arc seconds per pixel, and for the James Webb is 0.063. So there's a difference, but looking at the images at that number, I don't know how big will be the difference.
Therefore, with maximum DSF is very similar. You still have a factor of 2.5 between the wavelengths at 4.4 micron and 1.6 micron. So it's true that telescope
Oh,
is bigger.
then I missed the information about the wavelength difference.
Yes,
Okay,
one is
okay.
4.4
So
micron and the other
it
is
more or less compensates the difference in
telescopes.
DSM.
Yeah.
Okay.
So if I understood correctly, you did not validate the mergers in the JWST and HST images yourself, right? You used something from the Rainbow
Yeah.
database.
And it is a visual classification.
So why would you not why would you use simulated data to train your model in the first place, rather than using this data set of mergers available from the Rainbow database? Are there
Yeah, because
any
if you look at the
limitations?
Rainbow, it's very limited the number of objects classified as a merger. I think this number is 120, and this is 160. So training a model with this very limited number of galaxies, which experts classify as a merger visually, I think wouldn't help the model to take the most features possible into the merger process. I mean, there will be not enough features for the model to learn. That's basically.
Can I ask what you have learned from having both HST and JWST? Did you, I mean, if you've only used HST, would you have come to a different conclusion about how well your model was working, for example?
HST for what? For training?
Just in the sense, if you leave aside the JWST data and all the comparisons you made, would your conclusions about how effective your model is at finding mergers, it will be different, I guess. So I'm just wondering what you learned from having a comparison of two different data sets.
But these two.
No, not specifically that, in your whole setup. So your whole determination of whether you have mergers in HST images or JWST images.
Separately.
Well, you've got different results. So I'm just wondering if you what you gain by having both the HST and JWST in your analysis of how successful the method is at actually picking out mergers. So I would imagine that you may have just used HST. There's no reason particularly you have to use JWST as well.
Yeah.
So would you have changed your vision on how your program works by only looking at one? I'm just trying to understand what did you learn from looking at both JWST and HST as far as your method is concerned?
Yeah. There are a lot of things. If I would stop analysis here, for example, and never look at the James Webb, I would just end up summarizing the F1 score I got from the visual classifications. It's just that, but this is also probability. I mean, it's just visually given out by experts. So I took that as a true value, but doesn't mean it would be true value. So,
I'm just trying to understand why you used both data sets.
what do you mean both HST and James Webb?
Yeah.
Yes.
Oh, that was for the reason to do the analysis on the filter and the wavelength, the different
Okay.
wavelength, to see how the model performs for different wavelength ranges. And because the wavelength ranges are related to some physical phenomena happening at source, depending on the redshift, maybe that can tell me something. Maybe we can use the James Webb images for detect galaxy nurtures for some specific or in some specific circumstances.
Question of centering.
Yeah.
Is there another question? Other questions?
In this time, yeah. So just, I don't remember exactly whether you did this, but so for the tuning, based on the visual classifications, you are prioritizing on the F1 score, right? If you had chosen to, say, maximize the performance and precision, right? What did you do that? What threshold? My question is, what threshold do you get? Because you get a 0.05, which is, as you say, very, very low, right?
Yeah, but if we focus on precision, I think the main vision behind that is that we want to be sure that the mergers that we are classifying are real mergers. So I think.
So you currently are maximizing, or you're trying to maximize the performance of your network based on a combination of precision and completeness, right? And then you get a threshold of 0.05 that gives you the maximum F1 score value. I was just wondering, because I don't remember anymore whether you had tried to maximize on precision alone.
I didn't do that.
Okay.
I mean, I compute the precisions, of course, to get to the F1 score.
Yeah,
But I didn't do like analysis on the precision.
yeah, okay, that's fine, I just don't remember exactly what you did.
Yeah, but Berta told something like that in one of the meetings.
Yeah.
But then also we wanted to take into account that completeness, so
Yeah,
then we end up with the
Running
F1
out
score.
of time.
So it really depends what metrics you want to use and to say, okay, I'm happy with this for this analysis.
Yeah.
Maybe for another analysis, it's something else. It's agree.
Then I think we can finish. Thank you very much.